For the MOSFET bias circuit shown, we're asked what value of RD in kiloohms is needed to allow the maximum possible peak-to-peak signal swing on the drain without clipping. So an important part here is we need to find our RD. Another important part is that we need to find the max possible peak-to-peak signal swing on the drain without the clipping. We have these values here, and then we have another equation right here. We are to neglect the effect of channel length modulation and the body effect. Make sure we keep our MOSFET in saturation as well. And we're going to use the notes that are linked in the description below the like button on, I think, a page around 103. We actually have that previously that we've used. And these notes are going to allow us the equations for a P MOSFET in saturation. So the exact page for a PNP, which is what this is, in the forward active region, is going to be on page 103. So we're going to use those equations. Now, to start this off, we want to first list what we're solving, right? Well, we want to solve for our RD. Well, our RD is down here. So RD is going to be equal to, of course, we have the source voltage, which here is the VD. That's the voltage of the source looking into our RD, minus the base part, which is going to be our VSS, and this is all happening over our ID, and this is just simple Ohm's law. Now let's plug in some values. We're going to run into a problem here because we don't know our VD. However, we do know our VSS, but we're going to save this for later. So let's start working on what we don't know. I like to start with our ID, so that's what we're going to do here first. So for 2, our second step is going to be solving our ID. ID is going to be equal to IS, and that's just because it is a MOSFET right here. So that's the rules that we would follow. And this is going to be equal to, well, if we have our IS right here, we're going to be looking at this portion of our circuit. And so we're going to do the same thing that we did up here. We're going to take our VDD, which is the source looking into this, minus the base part, which is our VS, and this is all happening over our RS. Again, simple Ohm's law. Now we can start plugging in some values. So we know our VDD is given to us here in this equation as 6 volts. Yours might have a different value. We have 6 volts, and then we have a minus VS. And our VS, we don't know what it is yet. So we actually need to come and find this. Before we find this though, let's look at our RS. Our RS is given to us here as 7.5 kiloohms. And we're not going to expand this kilo. We're just going to leave it like that because we can translate it to milliamps in a second. So now let's solve for our VS. We don't know what it is. And VS, if we look at this node right here, it's going to be equal to the VG, right? Because we have some voltage out this way. And then the gate source. So VGS right here. So we're going to have VG plus the absolute value of our VGS. And now we can start plugging in some values. Well, our VG is given to us is 0.2 volts. We went over an example previously where this wasn't given to us, and we had resistors right here, and we had to make a whole part right here for our voltage. But that can be found in the playlist linked below the like button. So with this one, we're given our VG. So this is going to be equal to our 0.2 volts. Now our VGS is not given to us. We don't know what that is. So we're actually going to have to go and find it. So looking for our VGS is going to be our step 4. And in our step 4, we don't need to look too far because it's right here, right? We have our VON, which is 0.42, and that's equal to our VGS, and our VGS is what we want to find, the absolute value of it. And then we have minus the absolute value of our VT, and our VT is given to us as a negative 0.5 volts. So what we're going to do is we are going to just add the absolute value of negative 0.5 to both sides to get it to cancel out on the right, and then we're going to get a 0. And we should have a 9.2 if we add these together. And this is equal to the absolute value over VGS. And so we can just take this and plug this into here. So we have 0.2 volts plus 0.92 volts. And then this is going to give us a V of S be equal to a 1.12 volts. So that is going to be our V source. Now we can just come up and plug this into here. So from here we're going to have a minus 1.12 volts. And then this in turn is going to give us our ID, which is equal to our IFs, which is equal to 0.6507 milliamps. And that is going to be our current value. And we can take this and plug it into here. But instead of doing that, we're just going to rewrite it as 0.6507 milliamps. We keep the millis here because we're going to want this value in kiloohms afterwards. Next, we are going to look at step 5. And well, what is step 5? Step 5 is going to be finding this VD because we weren't given it. So step 5 will bring a little bit lower. Our VD, the way we would find this is by looking at the notes, and we'll be looking at the specific PNP part because we need to know the rules of our PNP and how it is going to function. Now, this can be found, I believe, a little bit earlier in the notes, and the kind of way we would write this is that we have our VDS, the absolute value of it, and that's for PMOS, which is what, again, this is, which is greater than or equal to our absolute value of our VGS, which is minus our VT, and then P for PMOS. That's what the P stands for. It's nothing specific, it's just P for PMOS, that's denoting what it is. And I believe the actual equation, or not equation, but this actual part right here where we can find this in the notes is going to be on page 81. That's where you would find this right here of the notes around there. So if you look at page 81 for this one, and then for these ones, we have page and then 103, and that would give us these equations right here. So now with this, we can keep looking forward. Notice how we have a VDS and a VGS on both sides. Well, we can cancel out the S part because really it's just VD minus the VS and then our VG minus the VS. So we don't need those. And now we are going to take away the absolute values. When we do this, we're going to have VD, and it's going to be it's going to be the VD max value. It's going to be greater than or equal to our VG plus the absolute value still of our VTP, and that's how we would write this. And now is where we want to plug in the values because we know them. So we are going to have our VD max, and I'm actually going to just do it over here. VD max has to be less than or equal to our VG. Our VG we found right here to be 0.2 volts. So we're going to do 0.2, and then we have a plus, this was given to us, so 0.5. And this is really negative 0.5, but it's the absolute value. So that means our VD max, the max value essentially can be 0.7 volts. So that is the value there. Now, when we solve for this, because we are about to solve for this, before we finish this, this would be like our step 6. We note that we have a VD minimum and a VD max. And our minimum is just going to be the VSS right here, right? Because that is the lowest thing it could be. So when we do this, we know that it is going to fluctuate like a sine wave. It's going to look something like this. We have more in the negative than the positive. That's why it's more in the negative here. But we do have some values right here, and then we have some values right here. So we're looking at the amplitude. Now we want to find the middle point. The way we would find our middle point is we would take our maximum and our minimum, and we would find the middle point. So our maximum here is going to be the 0.7. So this is our, and I'll write this out afterwards, but we have a 0.7 here, and then we want our minimum, which is the 7, negative 7. So we're going to have to do 0.7 plus a negative 7, and this is all happening over 2. And this is going to give us our VD bias. Now, the way we would write this, the equation for it, would be that we have our VD max plus the, it's plus, but it's also minus. It depends on how you're solving it because you don't want to take the difference. That's the important part. So right here, you're taking the difference of the middle part. And then we are going to have our VD minimum. And this is all happening over 2 because there's 2 different things. We want to find the middle of it. Now, this is going to give us that our VD bias is equal to approximately negative 3.15 volts. So that is our VD bias. And now we would just take this and plug it back into our original equation. So we have negative 3.15 volts, and then we know our VSS was given to us as negative 7 volts, and if it wasn't given to us, that is again in the playlist link below the like button, where our circuit looks a little bit bigger, and we have to make it smaller and look just like this. So this is what we're going to get, and now we can continue solving for this. So our RD is going to be equal to, if we plug all of this into a calculator, approximately 5.917 kiloohms. That was a long problem, but that is how we would go about solving it in anything like it. For other problems that are very similar, there's probably a video in the playlist linked below the like button.